I will talk about a subject which I, studied some years ago, and which was quite, I think, at that time popular in the community of stochastic filtering. In particular, addressing the question: how does the posterior distribution depend on the or the estimation depend on the prior distribution of a signal which we don't know. And my approach is somehow via some, let's say, parabolic ground state transform, which I will introduce later on, to relate somehow the problem of stability with spectral properties of some underlying, if you want so, Schrödinger type operator. So this is the goal. And in order to be able to describe this in a mathematical rigorous framework, I will first explain a little bit my approach in a general setting concerning contraction properties of Markovian integral operators. Then I will come to the problem that I will address in the application to the stability in the stochastic filtering. I give two general observations concerning the stability properties of the posterior. Then I will move on to time continuous signals, and then later on I will show that my stability result can be obtained uniformly with respect to time discrete approximations. Okay, so this is the framework I would like to work on. So in discrete time, so we have a Markov chain, x1, x0, x1, xs, on an arbitrary, first of all, measurable space, but later on this will be RD. And the transition probabilities should be written like this. So we assume that we have a sigma finite reference measure with respect to the transition probabilities of the Markovian transition kernel. And the density is just written by p of x and xn plus 1. So describing the step from xn, going from xn to xn plus 1. And pi naught always will denote the initial distribution of the Markov chain. And the basic assumption here, in order to make the things simple, is so I will assume that the density, the transition densities are bounded uniformly with respect to x and x prime over this state space of the signal. So that's concerning the signal. Then the observation is given with independent noise. So this is my assumption, and takes values in some space in the space RP. And the assumption can be written in this form. So it will be a function of the signal at time n plus 1, the observation, plus some additional measurement error E n plus 1. And we assume that we can write the distribution of the measurement error, so the distribution of the observation given the signal in state xn plus 1. We can write this with respect to some absolutely continuous distribution with respect to the p-dimensional big measure here, and g denotes the density, the likelihood function, if you want so. And here also the same assumption to avoid any technical difficulties, and it's also a reasonable assumption if you think of Gaussian estimates, that the likelihood function is uniformly bounded with respect to the state x and the observation y. Okay, so this is the framework I would like to work on. And the optimal filter, as you know, has been introduced already in several talks before. It's just the conditional distribution of, for example, the signal x at time n. So the conditional distribution of xn being in the state A, if A is a measurable subset, given all the observations from 1 up to time n. And the Markov structure of the problem allows you to write down for the regular conditional probability this well-known recursive formula. And so you see you have two ingredients here in this recursion. So first of all, we have this update according to the signal, working on the conditional distribution at time n. And then according to the new observation coming in at time n plus 1, the observation yn plus 1, we have this likelihood density which somehow redistributes the mass given by the prediction according to the signal of the posterior time n. Okay, So these are the two ingredients, and the goal is, well, we could write this first of all in an abstract form, which I will use later on, this notation. So we have this some kind of nonlinear transfer operator acting on measures, so depending on the incoming observation at time n+1 and the conditional distribution at time n. And iterating this, we see that we have this kind of concatenation of the operator T indexed by these new incoming observations and applied to the initial condition pi naught. And so in some sense, my goal or my interest is in understanding somehow the contraction properties of this transfer operator with respect to, in particular, for example, the initial conditions. And you see this involves, in particular, an understanding of how does the signal the Markov chain and also the likelihood, the measurement error influences somehow the stability property of the system. This is a generic problem because in Bayesian estimation, because the initial distribution of the signal is unknown, and somehow it's a generic problem to understand somehow the ultimate outcome of your computations with respect to your initial guess you plug into the algorithm you want to solve in order to approximate the posterior distribution. So that is a problem which is in some sense also is of a more general importance than just this application to this kind of stochastic filtering. Okay, here are some two general observations about the general dependence, so of qualitative type and also of quantitative type. So these are well known in the literature, and I start with this one. So this is, I think, the most used setting under which one can prove somehow the asymptotic independence of the posterior distribution of the initial distribution of the signal. So this is some kind of a mixing condition of the signal, and you can, for example, formulate some metric or some estimate on the contraction properties of the posterior distribution or of this nonlinear operator. For example, in this type, so this is some kind of the Bruching type contraction estimate, and this allows you to estimate the distance between the posterior distribution if we start with two initial conditions, let's say pi naught and pi naught tilde, with respect to the Hilbert metric. So this is a well-known result, has been exploited in various frameworks, I think first of all by Zatuni and Attar in the late 90s, I think, and then has been exploited by Leblanc also in several papers. Okay, so the Hilbert metric is of course a very strong metric. It dominates the total variation norm, and of course this is a very strong assumption because it implies somehow, well, it is essentially linked to, although it's not quite true, but to compact state spaces of the signal, basically. Another observation which shows that not only, how to say, the mixing properties of the signal influence the stability properties of the posterior, but also the measurement, is termed in this little observation. So bounded measurement error always implies stability. So for example, this is a statement you can formulate. If your likelihood is concentrated, let's say, on bounded set, that means if you make some observation, you can somehow locate the signal around the given observation, and then of course you need this mixing condition of the signal only locally on the support of the surrounding of the measurement y of the observation y, and well, if you, for example, this rate can also, this lower bound can be also observation dependent, then you can estimate as similarly to the previous case. If you start the signal again with, or the algorithm again with two different initial conditions, the posterior distribution with respect to the Hilbert metric with some, in this case, observation dependent contraction coefficient. So this is due essentially to Bujara, who was the first who formulated a result in this direction, I guess.
If A, they are positive,
this A need not be positive everywhere. No, not strictly positive. Of course, this is a strong assumption on the Hilbert metric, so you need to be careful what you are assuming here. So you assume that the densities somehow are bounded from above and below, so that means you are already in the interior of the convex cone in some sense. So you avoid any, how to say, degeneracy on the boundary. So this is the essence of this criterion. But basically you can summarize this result as better measurements improve stability. So these are the two ingredients, and the name of the game now is to somehow join these two influences and to be able to, how to say, quantify also the stability properties. Okay, I'm going back to my framework where I assumed I have a sigma finite reference measures for the transition probabilities of the signal process. So that means the transfer operator naturally reduces to an operator acting on densities, and with respect to the reference measure nu in this case. And so here is the transfer operator again written on the densities with respect to the reference measure nu. So this is the same as before. And the idea now is to somehow linearize this nonlinear operator T with respect to the density H. So this is the idea which I will now somehow apply and develop in order to get my results. And I call this parabolic ground state transform because this is in some sense the time dependent analog of a ground state transform, which is a method in mathematical physics and well known. And to this end I fix some initial reference density. Later on I will explain what this could be. For example, it would be, for example, in a trivial case of the Kalman filter, of course, which we only use as a study example, toy example, to check the results, a Gaussian density. And then we look at the forward propagation of this initial density with respect to the signal kernel of the signal process and the likelihood function. So the p hat here is now the adjoint of the transition probability acting, of the transition kernel of the Markov process acting on measures, or because we are now looking at of transition probabilities having a density, and we can look at this also as a kernel on the densities with respect to the measure nu, the reference measure. Okay, and the stability result is now from, so this is something like a reference model. So this could be, for example, what you assume here, and now this is your algorithm basically up to normalization. And the assumption now would be, or the situation would be now if you made the wrong initial guess, so that the true initial condition of the Markov process of the signal has nevertheless a density with respect to your initial guess. Let's call the initial density with H naught. Then under this assumption you can show that also the posterior distribution at time n of the signal, given the observations of time 1 up to time n, has a density with respect to this density mn hat, the solution of this forward equation, where Hn now is given explicitly by this quantity. And this is what I call a ground state transform, because the most important thing here is that this operator, now acting on the densities with respect to these reference measures, if you want so, is linear, acting on the densities, and it's a Markovian operator. So this is the main important thing. So you can somehow look at the spectral properties of this Markovian transition and try to understand now the dependence on the density Hn on the initial density H naught by studying the spectral properties of this Markovian operator. Well, so the contraction properties of this, as I said, ground state transform can be formulated in various function spaces, or you can try to get estimates on that in various function spaces. Probably the most natural at first seems to be LP spaces. So how to find the right, reference measures? Well, you have to solve somehow the Fokker-Planck equation associated to this ground state transform, and that means in this situation you have to solve again backward, a certain backward equation by fixing a terminal condition, let's say at time capital N, with some density Mn, and then going backwards in time using the same observations, you get recursive densities Mn minus 1 and so on. And then writing this as a product with respect to the solution of the forward equation and the reference measure nu, and normalize that, you get new probability measures nu star. This is something like a bridge, and this is in fact a solution of this Fokker-Planck equation. So the distribution of this ground state transform applied to nu n star actually gives the measure nu n minus 1 star, and you can iterate this. So this is the right, flow of probability measures adding stability in this setting. So these are the right function spaces, LP spaces, if you want to study these contraction properties of the ground state transform with respect to certain reference measures. So this is now clear from the first feature that this will be now a contraction on every LP with respect to 1 and up to infinity, and a more particular emphasis would be to look at the case p equal to 2, acting between the two different Hilbert spaces, and then you need to somehow estimate this contraction coefficients. So this has been worked out in various examples, including the time continuous case in papers in 2006 and proceedings 2007 and 2008, not only with respect to application of filtering, but also simulated annealing, for example. You can use the same idea, of course. The drawback of this approach is you need much, knowledge concerning the backward equation, not only the forward equation. And so the applicability of these approaches with respect to that extent a little bit limited. And so I moved on to study a different function space, and this will be a function just looking at the Lipschitz contraction property of the ground state transform. So in some sense what you're doing is you, in the LP space the contraction coefficients could be something like integrated gradient estimates if you want so, and now you somehow go to a stronger assumption on the ground state transform to pointwise gradient estimates, and these pointwise gradient estimates lead in natural way to Lipschitz function spaces. So this is the essential step which I did. Okay, so to set up a particular situation where you can formulate this, I will now, as I mentioned at the beginning, look at the state space Rd for the state space of the signal, and U should be the Lebesgue measure, so that should be the reference measure of the signal process. And then I look at the contraction, the Lipschitz norm of the function f with respect to a matrix A. This will also play some role later on, which I will explain. And okay, so this is natural. Now, of course, you can now formulate an abstract result. Suppose the Lipschitz contraction, well, first of all, suppose that the ground state transform is contracting on Lipschitz functions, and gamma k star is the Lipschitz contraction coefficient. Then, if we are in the same situation as before, we start our algorithm with two different initial conditions, but now of this type. So first of all, pi naught, sorry, this is the wrong way, but okay, it doesn't matter. Let's say with our initial reference measure m naught hat and some perturbed measure having a Lipschitz density with respect to our initial assumption, then we can write down this stability result in the total variation norm of the two posterior distributions we get by iteratively or recursively solving the recursion equation by this quantity. Okay, everything is fine, explicit. In particular, if the density, if the initial density H0 is bounded from below, which is a very strong assumption, of course, but due to the Markovian structure of the ground state transform, you have the same uniform lower bound now for all n. This is the main point. So that means this allows you to also, how to say, control this denominator here in this uniformly in n. So this is the point. So you really have then the contraction property encoded into this product. So this is an abstract result now. Now I give examples where you can make this a little bit more explicit. So one illustration, which is a simple case, is the Kalman filter. So it's well known, of course. So the signal is d-dimensional, the observation again as before p-dimensional. And the assumption which I will make here, although this is not necessary but eases the how to say computation, is that the covariance of the signal and the covariance of the measurement error are strictly positive definite. And then of course you all know that the main feature of this situation is that if you start with a Gaussian distribution, then the posterior will be again a Gaussian with these well-known recursive formulas. And here in this example you can explicitly write down the now the ground state transform if you start with this Gaussian density. So assume we start with the Gaussian density as a reference measure, then of course all later densities will be again of Gaussian type, where the covariance again is given by the recursive Kalman equations, and the mean is the same, that's clear. And the ground state transform is now also in this setting a Gaussian measure. And the Gaussian measure, well, you see the covariance as expected is independent of the observation, and the contraction is seen in the expectation of the ground state transform. So here's the dependence with respect to x, so that you have the contraction now with respect to this quantity here in the Lipschitz norm.
What is Lipschitz A in this case?
Later on. So that means, well, the ground state transform is just a convolution with this Gaussian measure, and the Lipschitz contraction is explicitly given by this one with respect to the A norm at the moment, okay? And now, and this is where the A comes in. If you want to look at the asymptotic stability result now, we assume that the system is controllable and observable, then we can solve this matrix Riccati equation. So we have a limiting Kalman matrix, a limiting filter. And if you now plug in exactly this limiting covariance matrix, then you have the right, in some sense, topology where you should measure the Lipschitz contraction. So this is the essence of this little computation. So you can show that this Lipschitz contraction coefficient applied to this covariance matrix converges with some geometric rate, which is explicitly given. All this is well known to this quantity. So that means you have the exponential stability of the Kalman filter, not only with respect to Gaussian initial condition, but also with respect to other initial conditions with this exponential rate. So this is the basic ingredient here. Now so that was the illustration for the time discrete case, and now I'm moving to the time continuous case. So, so here's the following heuristic. So we have a time continuous signal process here, and the observation y. And of course you know all these, so ET is a Brownian motion independent of the Brownian motion driving the signal. So this is the well-known Kaliampo-Striebel formula, which gives you a path space representation of the conditional distribution. I will later on use a robust version of this due to Clark and Krishan in a paper in PTIF, which is based on a robust version of this stochastic integral, basically, for continuous observations. I've looked also at the pathwise filter equation, which also gives you a robust representation of this one, but okay, I will stick to this one in this talk. The heuristic is now the following to study the stability. Well, formally setting the observation equal to constant yields that the, how to say, the which seems like forbidden, but okay. You see that the stochastic integral are showing up in this density, so the integral with respect to the observation vanishes, right? And so what you end up with is that the Kaliappo-Striebel formula reduces to this renormalized Feynman-Cut semigroup. And the asymptotic of this renormalized Feynman-Cut semigroup is well known. It converges in good situations to the ground state measure induced by the generator of the signal process and, well, the square of the density of the measurement matrix you look at. So this is the intuition, right? So this is well known, understood, and also the convergence here is well known, understood in many examples. For example, if you know you are, for example, in a situation where everything looks like a Schrödinger operator and the potential would be strictly convex, then you can also estimate the rate of convergence here towards this ground state measure here in various topologies, L2, and also with respect to the total variation norm. Okay, in fact, this observation is not so, how to say, forbidden, this heuristic, because you can make the following, how to say, you can think the following way. So suppose xt is ergodic, then of course you have, in the sense that, let's say, these time averages converging with arbitrary initial condition to the unique invariant measure, then of course any quantity of this type converges to the space average of G with respect to this. This is the invariant measure of the signal under my assumption, and that means that the observation process divided by t converges to the same quantity. So it's asymptotically constant if we divide by t. So that means the contribution given by this is of higher order for large t than the contribution given by the stochastic integral in this Kaliappo-Striebel formula. And so that means, in some sense, setting the stochastic integral here in this exponential to 0 is in some sense correct, but you have to work this out rigorously. So this is a rigorous result where you can also make some calculations. So the signal is assumed to be of this type, so a linear part and some gradient type part drift. And well, this is of course very limited. I will explain later on why this is the case, the assumptions. So the covariance of the noise in front of the Brownian motion should be strictly positive. And for technical reasons, in order to make this robust version approach work, we need that well, there exists a unique weak solution of the signal with any for arbitrary initial condition, and this Novikov condition is satisfied. Okay, I don't want to get into more details about this. The observation is now linear in X, and the measurement matrix is, the covariance of the measurement arrow is strictly positive. Then the main assumption, in some sense, that governs the stability property of the system is exactly encoded in this potential. So you see the interaction between the linear part and the gradient part. And what you see, forget about the B1 for the moment, what you see is in particular this potential, and this potential incorporates the measurement density and some quantities referring to the signal. And well, the assumption is that this is uniformly strictly convex function, of course. That's not so. The V is uniformly strictly convex, of course, right? So the Hessian can be bounded uniformly with respect to X by some symmetric positive definite matrix K. I'm sorry for that. the explanation for that why there's concave, because what we are interested in now is the following. So we termed the assumption in such a way that if we start the filter with a log concave measure, then the posterior distributions at all time will be again log concave. So this is why the concavity comes in. And if you know a little bit of spectral properties of Schrödinger operators, you know, for Braskamp-Lieb, for example, classical examples, you know that you can, for log concave situations, measure somehow the exponential rates explicitly. So this is Braskamp-Lieb results, type inequalities. So this is the main result now for the time continuous case. So assume we start now with the densities such that phi to the -1, which turns up in the drift part of the signal, times this density is uniformly strictly log concave. So this is now correct. With a certain lower bound kappa star, where kappa star is the solution of this Riccati equation. This is somehow the analog of the Kalman-Riccati equation. Then, well, if we have, I'm working now with this regular conditional probability of the optimal filter introduced by Clark and Krishan. So if I have a Hölder continuous path with Hölder index of order 1/3, I can somehow use time discrete approximations of the continuous time situation, and applying the result to the time discretized approximation, I get bounds which are uniformly with respect to the time discretized model in the limit, and this allows me to deduce the same estimates now for the time continuous case. So if we start the filter in the continuous time with, again, this kind of initial conditions, where these are the assumptions, and now I need a uniform lower bound here on the density H0 with respect to the reference density M0. Then I can estimate the difference between the posterior distributions or the conditional distribution in the total variation norm by these quantities. And kappa star is again the eigenvalue of this one. So this is related to the, in some sense, well, if one would not be there related to the ground state transform. Illustration for the Kalman-Busi, where there is only a linear part in the signal, where the signal is linear. Again, of course, well known. If you start the Kalman-Busi with a Gaussian, then it will stay Gaussian, where the covariance matrix satisfies this matrix Riccati equation, and the mean is a solution of this stochastic differential equation. And if you apply the previous result, then you can explicitly calculate the rates in this case, and they actually coincide with the rates that have been observed earlier. I would like to mention that assumptions I need are quite restrictive in contrast to somehow the existing theory on the Kalman-Busi filter, where you can of course use much more structure and much more information. The best result concerning the stability is due to O'Connor and Pardue in 1996, where they proved that if the system is controllable and observable, then we have this kind of stability, and also with an exponential rate which is quite related to the kappa star which I calculated here. But they use, of course, the explicit representation. Well, I skipped this here. This is a further illustration for the symmetric case. And I just mentioned that, for example, the signal, the criterion works in one-dimensional case completely, so you can deal with any nonlinear one-dimensional signal, because in the one-dimensional case, any signal is reversible, and you can explicitly calculate the quantities which are responsible for these stability rates. So here's this typical single noise to measure. This is a typical criterion. So you can see the more precise you measure the signal, the lower this gamma is, the higher, the more convex the potential becomes, the more stable the system becomes. And also the more ergodic the signal is, the more positive definite this quantity is, and you have the explicit interplay between the ergodic properties of the signal and somehow the measurement error here, so as it should be. And of course you can think of the multidimensional analog of that. I would like to close with the uniform stability for the time discrete approximations, and the proof is related to this Feynman-Katz representation of the transition probabilities. So you can rewrite in our situation the transition probabilities of the signal in some kind of Feynman-Katz integral with this potential V bar. Ut is the, remember, this Ornstein-Uhlenbeck process that somehow governs the linear part and the drift of the signal. And then of course the time discretization is obvious, so you can write Pt f of x as a limit of, let's say, fix n of n iterations of a single Markovian kernel Pn, which is given by just this straightforward approximation. So this is this integral operator, this Markovian, this integral operator. Sorry. And the observation can be, well, you have to be careful now what you are saying. Of course, you would like to apply basically the given the observation, the estimation procedure to the time discretized model, and well, this is in some sense the right way to look at it. So this is in some sense the time discretized observation, and then we have in the theorem 2 this kind of stability for these time discretized systems. So this is now, the signal is now time discretized, and also the observation in a suitable way. The regularity assumption are in such a way that everything, if the time discretization goes to 0, the time step goes to 0, then for a regular observation, Hölder continuous of order 1/3, of exponent 1/3, then it will converge to the regular distribution of regular conditional probability of the time continuous signal giving the time continuous observation. And where you can estimate explicitly the rates, and you see everything here depends on the time discretized model and on n, and it cost me some effort to find out that exactly these matrices indexed by n converge to the corresponding quantities in the limit. So this is really the correct result. Also, this rate of stability showing up here, kappa star n, converges as n tends to infinity exactly to the correct rate. And well, these are some quantities, I don't want to specify them. I would like to close with a short, how to say, lemma, if you want so, how to estimate the Lipschitz constant contraction coefficient over Markovian kernel in this setting. So the basic ingredient to estimate this Lipschitz constant in this setting is the point that the ground state transform always have this structure, you see. So we have a convex potential here, Vn star, and you can also estimate the lower bound of the Hessian in a quadratic form sense using basically these iterated equations which I showed you before, and you have well, the linear dependence on x. This is important. So x is the starting point because you just interchange. You look at the dual operators, and well, I've just looked at a simple case now. Of course, later on you have to plug in certain quantities here, but let's assume that q, n, and b are the identity, which is trivial, of course. But anyway, because then the system is also reversible, which is not necessary. Then the Lipschitz contraction is bounded by 1 over the Lipschitz constant, of Pn star applied to f is bounded by 1 over kappa n star square root of that times f, where kappa n star is this so-called dissipativity constant on the drifts of this system. And well, the argument to prove this is nothing else but a simple coupling. So you just look at the index by theta. Theta should be the starting point in some sense here of the Markov chain. So what the idea is to represent the transition probability, the transition kernel, as the ergodic measure of a one-dimensional of a diffusion process of gradient. A diffusion process, actually of gradient type in this case, but not necessarily. And well, the depends on theta is here this parameter, and then a simple coupling with the same Brownian motion gives you this a priori estimate, and this gives you in the limit exactly the contraction coefficient in the Lipschitz norm with respect to well, this is a mistake here. Of course, you know how to deduce from this estimate the Lipschitz contraction as mentioned in the lemma. So that's all. Thank you very much.
Questions, please?
Suppose you take the continuous time.
Yes.
If discretizing using order,
Yes.
You use the discrete version of the Feynman curves thing with the wrong observations.
Yes. With the wrong observation.
I mean, with your
yes.
coming from the continuous time.
Yes.
You apply your method for the discrete version.
Yes.
And get the stability of this discrete system.
Yes.
And then, can you extend the results to the continuous time in this way by getting some sort of control on the difference between the two
Yeah.
systems?
You see, I've chosen a particular time discretization. I don't know actually, but for this model, I would be pretty confident it works, so that you can control the error. But I'm not quite sure for the general case. So I've used this by purpose, of course. Of course, I'm aware that natural discretization would be Euler scheme.
Yes.
Of course.
They have all the ingredients in place.
Of course. Yes. So I cannot answer the question in generality. I think for this it should be.
Quick question. How high n depends on n, the last formula?
Oh, that's a dissipativity constant.
How it depends on n?
On n. I'm sorry. On n. T over n essentially. So T is the endpoint you want to like, and so that's the time step, if you want, so basically. So everything is explicitly written up in this contribution to this book.
Any more questions? Not then let's thank you. Yeah.